So, very warm good evening, everyone. So, yeah, this is the week 12 lecture of the impedance course. So, there's going to be a second last tutorial session. There will be one more actually. So, in that, I'll do the conclusion. I'll just give a brief summary on what you've learned in each chapter. So, yeah. Uh, so, I think nothing has been announced about that last class which is going to be taken. So, it was on 18th actually, this Thursday. I'm not sure, I am not exactly remembering time. I think the same time. So, you will get a notification on the same tomorrow. Okay. So, for this class also we'll continue with what we were doing. So now if you're looking to, we have to look into the porous electrode, and then about the different models for the film and the electrode surface. And finally, a nonlinear EIS. We'll look into nonlinear EIS on that last class, and then we'll give a summary also. So basically, for the nonlinear EIS part, that is 11th and 12th lecture, I mean 11th and 12th week lecture. It's mostly theory. I think only one derivation is there that's related to Franken model. If like someone had asked me about the the different step reaction. Is that what was asked? I'm not sure. Uh, Someone had asked me about in the non-linear years. I went through the assignments most basically theory-based question. So yeah, and also uh, I'm not sure, like, unlike the simple reaction mechanism where you can solve by hand and find the values, you need to either code to solve those questions, because it's also a function of the time, and that's how you express in terms of current density and you solve it. So even if I'm discussing the mechanism, we'll have to stop it at a particular point and leave the rest for the coding. So yeah, so I'll discuss in brief about nonlinear layers, but basically when I went through the assignments, I could understand there was only one or two numerical problems that is based on how to find the resistance charge transfer. Apart from that, everything else is theory-based questions. So yeah, so I also plan to discuss the assignment on the porous electrode, which is also purely a numerical based one. So that's my plan for today. We'll start with CP, we'll go with the porous electrode, just looking into how the derivation comes, and then we'll discuss the problems based on the based on CP and the porous electrode questions. Then also discuss briefly about the models, like the point effect model and the vacancy model. Yeah, so and then for the next class, that's the winding up session. I'll give a brief summary on all the classes, what all we have looked into till now, and then I'll also give a brief idea about the nonlinear years and just a glimpse on the Frumkin model. Yeah, so how much we'll discuss, it depends upon the time that's available for us. So yeah, so presently I'll go into the slide. And so I think my slides are visible. Okay. So yeah, that's the
Yes,
tutorial.
visual, visual.
Yeah, thank you. Yeah, thank you. So yeah, we are looking into the CP. So in real cases, modeling in like if you're using some software to fit the model that we had looked in third or fourth lectures, like we are using the capacitor and resistor or inductor to model a given impedance spectra. In all the cases, it's we as we saw, we cannot directly use a capacitor. In the sense, pure capacitor might not be giving us a good fit. uh, it is also, it might be a depressed circle. In that case, if you use a pure capacitor to model the circuit to fit the given circuit, it might not fit well. So in that case, we'll be using a constant phase element. So that is what is CP. So if it was actually a pure semicircle, what we expect is a good semicircle, and so this is going to be a part of the circle. If we extend it, okay, mine is also not a good semicircle, but still, it's so I hope you understand. So basically, what this is also not a good semicircle. So if what we'll have is something of this kind, like it's going to be a semicircle of a perfect circle, okay, and how to distinguish between them. So it can be something where your it makes an angle of 90 degree with the axis. So as you know, this will be the high frequency regime, and the this one will be the low frequency regime. So so in this case, if we get something of this form, we can directly use a capacitor to model the circuit. Capacitor in parallel with the resistor. But this might not be the case always. In a real system, it's not always possible. I mean, it's not true that always you'll be getting a perfect semicircle. There are cases where you'll get a depressed semicircle. So when it's a depressed semicircle, what does that mean is the it's not like the origin is passing through the axis. Instead, major portion of it is towards the down. Okay, so if you take in this case, the angle it makes with the axis will also be not 90 degree, it will be less than 90 degree. Okay, and in this case if you compare both, you can see that the resistance to the charge transfer value will increase in this case when compared to the initial case. So that's how we can distinguish between what to say, uh, like the pure capacitor, and in this case when we are this one will be less than 90 degree, and you can actually represent it by n pi by 2. Okay, and where the n value will be less than 1. Okay, it will be some fraction of pi by 2. So that's why I can say it's n pi by 2 and its n is less than 1. So you can see in both the cases the radius is different. In fact, this here the radius is more, and you can say that the resistance to charge transfer will increase. Okay, so now in this case, so here instead of capacitor, here we'll be using a constant phase element to model the system. Instead of resistor, instead of capacitor, you will be using a constant phase element to fit the model. I mean, fit the circuit. So, how is the impedance of you know what is the this thing of impedance of a capacitor? That is nothing but 1 by j omega c. Right now, what is the impedance of a constant phase element? What is the impedance of a constant phase element? So it will be something of the form 1 by j omega raised to n into y naught. So y naught is an arbitrary constant. Okay. This is the difference between the constant phase element and the capacitor. So now the question is, for different value of n, you can approximate its behavior to different things. So who can tell me what will happen when n value equal to 1? So what behavior will it resemble to if the constant phase element has the n value equal to n?
Maybe a perfect semicircle.
Yeah, so n value equal to n, you can reduce it to something of the form 1 by j omega y naught. And in this case, y naught is a constant. Okay, so you can say it is similar to this capacitor. Okay, so here you are approximating ZCPC to a capacitor. That means you are having a perfect semicircle. Okay, now what will happen when n value equal to minus 1? What can it be approximated to?
Like register.
Resistor, is it? What will happen when n value is a negative value? So when n value becomes a negative, this in the denominator basically it becomes inverse. You have for n equal to negative 1, it will be 1 by j omega raised to minus 1 into y naught. Okay, so what happens? I'm taking j omega inverse, so it's going up. Now you can say
Inductive.
inductor. Yes, so you can approximate this to be equal to L value 1 by y naught is similar to L, that is resembling L, so it is something of the form inductive behavior. In that case, it is showing an inductive behavior. Now, what about the case when n equal to 0.5? There will be of the form 1 by root j omega into y naught. So basically it is root over j. So from that you can say that it is going to be complex number. So yes, so this n value is something that varies between uh, 0 and 1. Okay, so yeah, so y naught value, and now coming to y naught. So n value will keep varying between 0 and 1. Now how about y naught? Y naught value should be such that the final unit of ZCP, what is the unit of the impedance?
Ohms.
It's ohm centimeter square. You should never express impedance. I mean, there are papers, journals in which you will see that the impedance is expressed in terms of ohms. Basically, you are reporting a value of you do some experiment like a metal immersed in electrolyte, and you might be a gold electrode or something in some ferroferry solution, and you say your resistance to solution resistance is something like 9 ohms. But how can I say, or how, if another person wants to recreate, I mean, repeat that experiment or wants to do it, how can the person know what is the area exposed? Because the impedance or the resistance is also dependent upon the area which is exposed. If your area is small, correspondingly, your impedance will be small. So it is always better when you are reporting it in papers. It is better to always report it in ohm centimeter square, so that when a person who is reading it can have a better clarity on like how they have to repeat the experiment or how they should do it if they're trying to do your work or something like that. When you report it in ohms, especially if some battery performance and all, you're saying oh, impedance is small, and someone wants to compare it with their own material, it becomes difficult. Always when you do it with respect to this much area, I'm getting this much or something like that, ohm centimeter square, it is better, easy for another person to compare your performance with some their performance or something like that. So finally, the impedance of, so here also constant phase element should have a unit of ohm centimeter square, and you know that the n value will keep on changing, so j omega, this unit will keep changing. Okay, so similarly y naught value will be such that the finally the unit of ZCP will be ohm centimeter square. Okay, now what does the CP behavior arise due to? Well, like till now, whatever we saw, we say it is a pure semicircle, but that's not the case. You get something, you can get something which is a depressed circle. Now, what is the reason for that? So, people usually say that the CP behavior is attributed to the roughness of the electrode. See, roughness of the electrode plays a very important role. If you are working with a metal in an electrolyte and you do not, you polish it differently each time, if you would have noticed that your impedance value will be different. It is difficult to get a reproducible data on in this impedance if you are not polishing the surface properly, in the sense it should be done in the same way each time. You should, like when you repeat the experiment over a period of time, you will itself understand, yeah, this is how I'm doing. Like when you are over smoothing it, the behavior will be different. If it is very rough, the behavior will be different. So each time with the same electrode and same electrolyte, concentration of the electrolyte will all be same, but still you will be getting different value. That can be because of the difference in the roughness of the electrode. So roughness of the electrode plays an important role in the impedance values you get. So here it is reported that the CP behavior when compared to what to say, when compared to the electrode surface, I mean CP value and compared with the capacitor value, pure capacitance value, the difference is because of the roughness of the electrode. So for our naked eye, the electrode may look very smooth, but it might not be the case when we are actually looking it under SEM or something. So there can be some scratches. So because of the scratches, there can be some ups and downs. So it depends upon how much is a scratch. How deep is a scratch. Sometimes it can be so much. So again, so there can be within an electrode there will be different levels, and each point will be different energy levels. So it may look smooth, but there can be microscopic roughness. So you can have that's what you cannot see with your naked eye. Instead, you will have to do some SEM or something. So because of that, there will be some microscopic roughness, and this microscopic roughness can result in different energy levels, and this will result in CP behavior. Also, it can be in 2D form or in the three-dimensional form. Okay, so that is what was told. So when you have different energy level, the CP behavior at each point will be different. So when CP behavior is different at each point, this means the current distribution at each point will be different. I mean, because of the different energy level, I can say that in another way, that is the current at different points, current distribution at each point is different. So because of that, the CP behavior will arise. Okay. So yeah, this is what we looked into now. So now the next thing, you can expect problems even for your final exam. There are two models which are used to describe or define the CDL. The CDL value, just wait a second. So the first one is, I do not know how to pronounce this. Hugh and Manfield. So you can learn these formulas by heart small, and also you can expect questions based on that. In the assignment, the questions are there. You can expect similar questions even for your final exam. So please learn the formulas by heart. Okay. So CDL effective Y0 raised to 1 by N RT raised to 1 minus N by N. Okay. So this is the formula using Sue and Manfield. Now similarly, you also have formula based on Bruck's formula. Okay. Which says CDL effective equal to 0 is 1 by N. There are some empirical formulas which I used to find out the effective CDL value, and this is how it is formed. So all the terms are known. You know what is RT, R solution resistance, Y0 value, N value can be between 0 and 1. So based on that, there are two formulas. One is by Sue and Manfield, and the next one is by Bruck. So yeah, these are the theory questions that are in the. I mean, based on this, we have I mean, few problems to do. Then we will discuss about the porous electrode. Okay. So yeah. So the first problem is, consider a system which exhibits CP behavior. Okay. Given the R solution, this is 100 ohm centimeter square. RT and RP equals to 20 ohm centimeter square. CP parameters are given. Y0 value is 5 into 10 to the power minus 5 ohm inverse centimeter square inverse and second raised to n, and the n value is given as 0.8. You have to find out the effective capacitance as per the Bruck's formula. Please do it. And the unit is told in microfarad per centimeter square. Please do. So if anyone has any doubt on the formula, it's few slides. Okay, Bruck's formula. So you have to find the effective capacitance, CDL. Okay. If you know the Y naught and all, so Y naught raised to 1 by n. So basically it is substitution, and if you are doing it properly, you will get the answer. Please be careful with the numerical problems, because if it's a direct problem, this is like if you do, you can score a lot of marks. Please do it and let me know. I'll give you a couple of minutes, 2-3 minutes, and we'll discuss.
So, uh, double
Yeah.
layer capacitance and this equivalent capacitance both are same.
No.
So
Which one?
here
Sorry,
in
sorry, sorry. I didn't get you. Double layer capacitance and yes, equivalent capacitance or double layer capacitance both same, corresponding to CP behavior. I'm trying to correlate.
Point 12,
Sorry, point.
12
Please check the.
micro.
Still you have to check it. There is a mistake. Anyone else have got a different answer?
11.3, I think, right?
Okay. Any other answer? Okay. Yeah. So what is the Y naught value? Y naught value is given as 5 into 10 to the power minus 5, right? The whole raised to 1 by 0.8. Okay. 1 by R solution, it's 100 plus 1 by RT, this is 1 by 200. It's 0.8 minus 1. So what do you get? You will get I'm getting 1.201 into 10 to the power minus 5.
But we need it in microfarad,
Yeah,
right?
yeah.
So,
So I'll
so
multiply
it's
by,
point.
so this in farad. You needed it in microfarad. So what do?
So 0.12.
You have to multiply by 10 to the
So
power
square.
6. It's in farad. You're converting it to a smaller unit. So you'll have to multiply it by 10 to the power 6. So it's in farad. You have to convert it into microfarad. So basically, it's like you have something in meter, you're converting to centimeter. What you do, you multiply by 100.
Okay,
So
okay. That means it will be 12.
yeah, so it is 12.01. So here the answer is 12 point. So please don't make a mistake with the units. Be careful because some questions can be direct. So don't lose marks unnecessarily for the exam. Be careful. So your answer is 12.01 microfarad per cent. Sorry, not per centimeter. It's microfarad centimeter square. I'm sorry. It's farad centimeter square, microfarad centimeter square. Okay. So I hope no one has any doubt in this question. We'll move on to the next question. So it's similar to the previous one. So I mean it's the same thing, I guess. Yeah. So consider a system with CP behavior. Solution resistance value is 100 ohm centimeter square. RP equal to 200 ohm centimeter square. CP parameters Y naught is given as 5 into 10 to the power minus 5 ohm inverse centimeter square inverse time raised to n, and n value is 0.8. Suppose to find out the equivalence capacitance as per the Sue-Manfield formula. So what is the Sue-Manfield formula? Please try doing.
Is 0.89 into 10 to the power minus 6 microfarad
Sorry, I did not
centimeter.
hear. Your voice is breaking.
8.89 into 10 to the power minus 6
8.89.
microfarad into 10 to
Okay.
the power minus 6
Okay. What are others getting?
microfarad centimeter square.
What are others getting?
It's a
Please.
15 point, let me say, 15.811 microfarad centimeter square.
So the first person you had made some mistake. Please. Okay, we'll discuss that. Okay. So Y naught value is 5 into 10 to the power minus 3. Okay. Raised to the power 1 by 0.8.
Yes, ma'am, I had made a mistake.
Yeah, that's why I told.
It
Please
is
speak.
15.81.
Yeah. So like you all know that for your final exam you will have to use the scientific I mean the one which is shown in the PC. Mean, it will be shown or it will be shown along with that exam. There will be a calculator on the screen which you have to use. So at least when you're trying to solve few questions before the exam, try to do it in that one. Okay, because calculator we might be able to get it very easily because you're typing, we are able to save everything and do it. So that's not possible when you're using the calculator on the screen. So when you're practicing a few days before the exam, start using that calculator instead of the phone or calculator which we have in hand to do the calculation. Why? Because people one of the reasons why people do not get enough time in exam and also make mistakes in the problem is because they do not have a exposure to how to use the calculator on the screen. So the bracket issue comes, square root issue comes. So like you may assume if we are doing it over here in normal calculator, we just put a square root and everything we type gets into that. So that's not the case when you're using, like there are some differences when you're using scientific calculator in our hand and also on the screen one. So that difference is there. You can't do a large calculation there. I mean, then it's difficult to identify the mistake. So it's always better, and also becomes time consuming when you're doing something which we're not sure about. When it will consume a lot of time, you won't be able to finish the exam properly. In the sense, you might not get time for revision, or you might not be able to finish all the questions. So it's always better when you're starting your revision for the final exam, few days before itself, start using that on-screen calculator, so that will be helpful for you. Okay, that's just my suggestion, because you might have a tendency to make more mistakes if you're doing it by hand. Okay, find into 10 to the power minus 5 into 1 by raised to 1 by 0.8. RT value is 200. Okay, so when you solve this, okay, when you solve this, you're supposed to get 1.5811 into 10 to the power minus 5 farad centimeter square. We'll have to multiply it by 10 to the power 6 to convert into microfarad. You'll get 15.811 microfarad centimeter square. Okay, now we'll move to the next question. In the same system, if the effective, Y naught is 2 into 10 to the power minus 5 ohm centimeter square, ohm inverse, centimeter square inverse, time raised to n, and effective capacitance, R solution, RT and RP are same as before, then as per Brugg's formula, what is the value of n? So you're supposed to use a Brugg's formula. Okay, please start doing it. You'll have to use Brugg's formula. R solution, RT and RP are same as before. So R solution equal to 100 ohm centimeter square RT and RP are 200 ohm centimeter square. Okay, you have all this, and you're supposed to use a Brugg's formula. Please do it.
In value, ma'am.
Yeah, you have to find out n value.
Okay,
The,
okay.
the question is that, yeah, effective capacitance is also same as before. So that is, your CDL value is also given as same as that of before question. You're supposed to find out the n value. So it is 15.8 microfarad centimeter square. Yeah, as per the Brugg's formula, you have to find the value of n.
Zero 0.928.
Okay, someone said it's 0.928. Just wait a couple of minutes just to see if someone else gets the answer. Any other answer? So yeah, what's the Braggs formula? Braggs formula is CdL by naught is to 1 by n RT is to 1 minus n by n. So CdL value is given as 1.201 into 10 to the power minus 5. Be careful, you have to convert. That's why I purposely gave it as 15.8 microfarad. Not here. Sorry, just wait a second. Okay, this is not the formula you have to use. Sorry. You have to use so this value will also change. This one which I wrote is Sue and Manfield. So this is not the formula you have to use. Instead, I have to use the other formula. So not this one, I have to use this one. And here the effective CDL value is 1.201 into 10 to the power minus 5. So this one is wrong, what I wrote over here. I wrote 15.8, but that's wrong. Why? Because they have asked with respect to question 1. Question 2, we are using Sue and Manfield. Okay. The formula will be CDL equal to Y naught by N RT raised to okay. The value is 201. So what can you do? You'll have to change values of N and check that for what value of N. So you can either do 0.1, 0.3, point something like that. You just change the value of N and check for what value of N this entire value is approximating to 1.201 into 10 to the power minus 5. Once you get that range, try to bring it lower. So if I understand that the value is between 0.9 and 0.9 and 1, what I have to do? So I'll put 0.9 value for n. I'll get some value which is closer to this one. I can put 1 also and find some value closer to that. Then try to do 0.9, 0.91, 0.92, 0.93. So again you'll understand. So based on that, you will get. So finally, even I got the same answer, 0.928. This is the n value. Any doubt?
Can we do it logarithmic by taking the log? So power
Yeah,
should be
yeah,
that.
you can do. You can try any method which is comfortable for you. So I had used actually calculator to do it, but again for your exam you
Okay.
won't be allowed to take it. So yeah, so that case, you will have to, yeah, you can go for logarithmic, or you will have to change the value and see where LHS and RHS will be equal, and then you will have to
Understood.
In case if we take calculator, then logarithmic, then how it will be done?
So it will be this one. So here you have two terms. Still, you will have to change, keep changing the value and check. This one I can, so if this entire thing I can treat as A, this entire one. So basically, you see 2 into 10 to the power minus 5 into raised to 1 to the power n. That's one term. I'm taking that as A. And this entire thing can be B to the power B. And this can be taken as A to the power A. Is that clear? You have A, which is 2 into 10 to the power minus 5, which is raised to your power 1 by n, which I am equating as A. Just for easiness, I am showing you. So this entire term 1 by 100 plus 1 by 200, you can simplify, you'll get a value. That is B, which is raised to another power 1 minus n by n. So that I am representing by small b. So here also you have something. So let me say this is C. I can do log C equal to log a to the power a b to the power b. Okay, this of that form. I hope you understand. So a is 2 into 10 to the power minus 5, just raised to power 1 by n, which is represented by small a. B is 1 by 100 plus 1 by 200. It's raised to power b, small b, which is 1 minus n by n. Okay, I'm applying log on both the sides. So log anything, I mean of x, y, it is nothing but x log x plus log y. So same thing goes here. So this can be again written as a log a. So these are all it's already there. I can write that like this. So again, if you simplify to this form, again you will have to, you get something in a simplified version. Basically, if you're using that screen calculator, it might become easy for you. You don't have to do raised to power something. Okay, that's only simplification. Again, you'll have to substitute for different value of n and check where your RHS will become equal to LHS. That's how you'll have to, do it. Okay. Yeah.
So what would be the tentative range of this n?
For this question,
No, journal, in the journal it has a limitation,
yeah, it is less than 1.
Between 0
like
to 1.
0 to
Uh,
1.
Not really 0, minus 1 to 1. Even I wrote wrong in the previous slide, because if I'm so yeah, if it is, if the value is minus 1, it will behave like an inductor. So yeah, minus 1 is also a case. So like if it has to, for a, it can replace a capacitor, pure capacitor, in case the value varies between 0 and 1. Okay. That will be the range for it to behave like replace a capacitor, pure capacitor. Now, the next question, CP behavior may be expected when the electrode has two-dimensional heterogeneity, three-dimensional heterogeneity, both of the above, none of the above.
Both of the above.
Yeah, so that's already, so it is both of the above. In the given system, EIS was acquired at different DC potentials. The double layer behavior is represented by CPE. As potential increased, the magnitude of CP parameter Q increased. What is the exponent N is expected to?
Decrease.
Yeah, it's decrease. So that's based on the formula. So Z equal to, so it's saying that the magnitude of Z or Q, okay, the magnitude of CP parameter is increasing. So that means this entire term has to reduce, the denominator has to reduce. That will be possible only when n will decrease. Okay. Yeah. Now the next one is based on porous electrode. Before looking onto that, we'll just discuss about the derivation. So next, so till now, whatever you looked into, we expect it's a planar electrode. But what will happen if it's a porous electrode? The impedance behavior will be different from that of a planar non-porous electrode, because you will have minute pores in it, and it's not exactly happening on the electrode electrolyte interface. It's happening across the pore, and the behavior will be different. In fact, we will have to take into account the pore number also, or the pore density, to account for the reaction happening. Okay, so the first thing is the impedance response of a porous electrode will be different from that of a planar electrode. So you consider an electrode like this, we cannot say that the reaction happens here alone. You have different pores, and the reaction happens across each pore. Okay, and if you take this, this is the exposed surface. Okay, this side is the exposed surface to the electrolyte, and the reaction can go up to this end because of the pores. It will happen across the pore. So here I'll take x as 0, and it can go up to x equal to L, right? So why does that happen? Because it's porous, and the electrolyte can flow in through this, and you can expect reaction happening anywhere across the porous electrode. So it will start from x equal to 0, and you will have the reaction up to x is equal to L. So the reaction is spanned across this entire pore. So that's what we have to take into consideration. Can anyone tell me which is a model which is used to describe the porous electrode? It has a name. So it is nothing but de-Levy model. So that is what is used to describe this porous electrode behavior. Okay. So it has some assumptions. We start discussing about the assumptions, and then we move on with the derivation. So what's the first derivation? Assumption in the sense like what are all considered. So the first one, in real case the pores can be of any shape, but here for the derivation we strictly say that these pores are cylindrical. So it's cylindrical pore. That's the first consider. That's what is considered first. That's all cylindrical pore. Next we say it is specifically for metal electrode, not for any other. Okay, it's metal electrode. And one more assumption which we take is that potential is same everywhere. The same everywhere. Okay, and we consider it's along this direction only into the pore, or in the sense the axial diffusion is not considered. Axial diffusion is not considered. Okay, so based on this what to say considerations, we start the derivation. So what do we say? I hope the assumptions or whatever we considered are clear to you. So now what we say is, sorry. So we assume that ideal behavior is enough. Ideal, ideal, ideal capacitance behavior is considered, okay, across the pole. So if we are assuming, there's also another consideration, like we are saying that across the pole it's only ideal capacitor behavior, there's no CPE effect. So in that case, what will be the specific impedance of pore wall electrolyte interface? That is at x equal to 0. How will it be? What all you have here? You have some reaction happening, and at the electrode electrolyte interface there will be capacitive behavior, right? So that's it. So the both will, it will be something of this form, right? You have a Faraday reaction. I mean anything. Might not be a pure state, can be anything. I can say there will be a Faraday reaction and there will be a double layer capacitive behavior at the electrode electrode interface. So basically it is in parallel. So it will be nothing but inverse. It's in parallel. So inverse of Z naught will be inverse of CDL plus inverse of ZF. So I'm just taking it up, and if I'm saying it will be ZF, sorry, is anyone telling anything? Is there any doubt in what I've written? So the total Z naught value will be nothing but it will be the sum of inverse of ZF. How did you get that? I've just simplified and written. How is that coming? You have both of them in parallel, so it will be 1 by Z naught equal to 1 by ZF plus 1 by impedance due to capacitor. This will how it will be. So if I am taking Z naught or inverse of this, what will it be? Inverse of this entire thing. 1 by ZF I have written as ZF inverse plus Z, 1 by ZC is nothing but J omega C, right? Raised to, I mean inverse of that. So that's how you get that. So this becomes your first equation. Now after that, we are saying that there is no Faraday reaction happening. This is an assumption. So what? There is no Faraday impedance reaction means ZF will be infinity value. Basically nothing is happening. So it's offering infinite impedance. So this value will be 0. Right? Let's clear it. Now I'm defining few terms. few terms in the sense. One is del. So del is the specific resistivity of electrolyte. That is ohm meter square. Specific resistivity of electrolyte ohm meter square. Okay, and L as the length of the pore. You have a pore whose length is L. And you have R, which is the radius of the pore. So potential drop across the, so you have a pore which is of length L. Okay, this length is considered as L, and these pores will have a radius. Here you can see this small radius will be R. Okay, you have R as the radius. Okay, and you have the specific resistivity of the electrolyte as del. Now what I'm doing is I'm finding out the potential drop across a short distance del x. Basically, I'm trying to find out what will be the potential drop across a small distance of pore del x. I mean, then I'll be extending that to over the entire length of L. Okay, in pore, which is given by del E. So across the pore, there will be drop in the potential, and I can write that as it is I. Okay, it's I into R. Okay, correct. Now, what is R? You all know resistance formula is rho L by A. So rho is the resistance of the electrolyte. Okay, L here means it's across a small distance del x, right? So rho del x, rho L by A. So area is that of a pore. So here you know the radius. So you know that your resistance across that will be pi r square. Sorry, yeah, pi r square. So if I substitute that over here, I'll get minus yeah. Did anyone speak? You get a formula like this. Okay. So you see del x this side, right? I'm taking that to the other side. That is del E by del x. So small change in the potential because of a small change in the length of pore. So this is nothing but it is same as d E by dx, right? Which will be nothing but minus I rho by pi r square, right? You have an equation like this. Now you have to find out what is del I. Okay, what will be the current that is passing through the cylindrical side wall of length L. So first we found out what is the potential drop across the pore. Now we are finding out what is the change in the current. Okay, so that will be, so we all know V equal to Zi. So any change in current will be because of the change in the potential. So if I am writing that in the form of differential, it will be del V by Z equal to del I. You understand? That is, across the pore, if there is any change in the current, that can be attributed to the change in the potential over that length. Okay. So del I can write it as minus E. So again, we are expressing everything in terms of centimeter square, right? So here you have ZDL, which is the change in the impedance, okay, into 2 pi r delta x, which accounts for the area. This change in the current is across the side walls. Okay. Now again I'll do di by dx. Why? Because I have a change in current across the small change in x. So that
Excuse me,
yes, tell me.
how you have written delta I is equal to minus E into 2 pi r into x, 2
Okay.
pi r into delta x.
So here we are accounting for the change in the current across the side walls. So
Side walls
yeah,
is 2 pi r.
that is the area
No, 2 pi r is circumference. No?
into x delta x. So it's across the side wall. So this 2 pi r IR will give the circumference, right? And
Right.
into delta x. So what does that become?
Which is,
You're taking into account that. So then
that
it
is
becomes
area
like,
of inside that pore means
yeah,
in a
a side wall.
inside side walls inside
Side, yeah,
side walls.
yeah. So basically you take the circumference and you multiply it by a small thickness.
Yes, delta.
Okay. So again I take the delta x the other side and I get minus E by ZDL into 2 pi r. So what is this ZDL? So that is the impedance. So we already told there is no Faraday impedance, there is only the impedance is the capacitive impedance, and that's a pure capacitor. So we know ZDL, nothing but it is 1 by j omega CDL. I substitute back that over here. Okay, into 2 pi r. So you get two equations. One is d by dx and another one is di by dx. So sorry, just wait. Yeah. So you get an expression like this, right? Now, you have an equation like this over here, right? dE by dx equal to minus I into del by pi r square, right? This equation. I am differentiating it with respect to d by dx. Okay. When I differentiate it with respect to d by dx, I'll get something like d square E by dx square into minus of del is a constant, pi r square is a constant, that will move out. You'll have I, di by dx, right? You'll have d square, I'm repeating it again, d square E by dx square will be equal to minus di by dx into del by pi r square, rho by pi r square. Okay, so you already know the value of di by dx from this equation, right? You can substitute there. Are you following that? So if I do that, I'll get d square e by dx square. I'm differentiating this equation. Okay, d square e by dx square is equal to minus I into rho by pi r square. And from above, you know di by dx is minus e into j omega c dl into 2 pi r. Okay. Substitute that. You have another minus. Di by dx is minus of. So this minus and this minus will go. It becomes plus e j omega c dl 2 pi r. So again, if I write in the next slide, or I'll write here once and I'll take the other side. You have E into j omega c dl into 2 is there and rho is there by r. There you have d square e by dx square. Right? I'll rewrite it again. Okay, so if I write this again, square e by dx square minus so this is of the form d square y by dx square minus m square into y. So here the m value will be nothing but 2 rho j omega c dl by r. Okay, and your solution will be of the form E equal to c1 e raised to power mx plus c2 e to the power minus mx. Right? Now you have to find out
Here, why we have made second differentiation d
where
square
we,
dy dx square? Why we? What is the purpose of that?
so
Which is second.
here you have dE by dx as a function of I, right? Similarly, you have di by dx as a function of E. So it's a first order equation and you have two unknowns. So you cannot proceed properly. You cannot proceed in that way, right? Either because it's a first derivative, if you need to have only one, that is one variable, that is I. Here you see you have di by dx as a function of E and you have dE by dx as a function of I. So I want to make it in terms of only one variable. Okay, so what I'm doing is I have d by dx equal to minus I into rho by pi r square. So what I can do is I can substitute for I. But how to substitute? I know only di by dx. Okay, so I'm double differentiating it. So it becomes d square e by dx square equal to minus di by dx into rho by pi r square. Then I'm substituting di by dx value from here. Okay, then I have some double second order equation. I have only one variable, that is E, and if I'm rearranging it, I get something of the form d
Then
square
it is
y.
equated to 0.
Yeah, because
It
you
is equal
see
to
d square E by dx square equal to E into 2 rho j omega c dl by r. So I'm bringing this entire thing to this side. So I've written something like A equal to B. Then I'm taking B the other side, becomes A minus B equal to 0. Whatever is there on this side, I'm taking to the other side. So what is there on the right side of equal to sign? 0. Then I'm making it into the form t square y by dx square minus m square y equal to 0. So basically the same as writing d square y by dx square equal to m square y. So if I'm taking it to the other side, that 0 goes. If I'm bringing this side, that comes as 0. So after that, I give a value for m, that is 2 into rho j omega c dl by r, the whole raised to 1 by 2. And for such a problem, just wait a second. So your value will be E equal to C1 e raised to mx plus C2 e raised to power minus mx. So now what you have to do? You have to find C1 and C2. So you need to know the boundary condition. So what are the boundary condition? You have a pore. You have at one side x equal to 0 and another one is x equal to L. That is the end of the pore. So what is at x equal to 0? That is where you apply potential E equal to ESC naught. Okay, and across it there is a deterioration of the potential. Okay, and at the end it will be like no reaction is happening. So you can say d by dx that is equal to 0. Okay, so these are the two boundary conditions that you apply. Now if I'm applying, so you know what is the E equal to C1 e to the power mx, C2 e to the power minus mx. Okay, now I'm applying the condition at x equal to 0, e equal to just wait a second. Yeah. So here you have, when you apply this, you have e raised to mx and the that other terms going to 1. So you have ESC naught equal to C1 plus C2. Okay, so this will be the first condition. Now to apply the next one, that is dE by dx will be equal to 0 at x equal to L. So for doing that, you will have to simplify. Okay, so what you can do is you will differentiate this one. So you will get something like dE by dx. Please do it and let me know what are the C1 and C2 value. I'll give you a couple of minutes. M is common, you can cut it out. You know what is the relationship between C1 and C2? C1 plus C2 equal to EAC naught. So you can substitute in terms of either C1 or C2 into this equation. You can use this one, substitute in this one, and you will get what is C1 and C2. Anyone has got? So once you do this, you will get C1 as EAC naught minus ml okay, and C2 will be EAC naught minus C1. So when you substitute it, you will get something like you get this. Okay, substitute back into E, you will get something like EAC naught e to the power ml plus e to the power minus ml minus m okay, this by 2, this by 2. Okay, if I do that, finally, this is to simplify it. Okay, EAC naught now is HM L minus X. You get an equation like this. So now you want to find out a potential. So I hope this equation is clear. Now I want to find out a potential gradient. So now whatever equations I'm going to discuss are very important. Okay. So you want to find out the potential gradient across the pore. How do I do it? It will be nothing but dE by dx. Okay. Now, what will be the potential gradient at the surface? The surface in the sense at x equal to 0. So this, you can expect problems from this. Can anyone tell me what is the potential gradient at the electrode surface? Can you try and let me know? I'll give you 2 minutes or something.
So 0.
Is it? Please try. It's not 0. So this is the equation. You will have to differentiate it with respect to x first and then substitute x equal to 0. You can expect a question where you're asked what is the potential gradient at the electrode surface. Have you got? Anyone? What is d by dx? Can anyone tell? I'm differentiating it with respect to x, this entire equation. This is a constant, it's not a function of x. This is a constant, it's not a function of x. Then which term will keep changing? It will be cos hm into L minus x, right? That's a function of x. So how will it become? So let me write down all the constants or okay. I'm differentiating cos hm into L minus x. What will it be? It will be sine hm L minus x, and you are differentiating the x again, so you'll have minus 1. Now this at x equal to 0, right? When x equal to 0, it will become sine HML, right? You have something like cos HML also below that. So you can simplify it as, so when this differentiate cos HML minus x, you will have sine HM into L minus x, because you are differentiating cos, you have an m, so you will have an m outside, and minus 1 because L minus x. When you're differentiating it, you'll get negative 1. So you have minus m EAC naught. Is that clear? Is that clear? Now you know what is d by dx. That is the potential gradient at the electrode surface, right? Now the next thing is, that's almost like Next thing is you have to find out what is the current. How will you find out? You know the potential gradient at the electrode surface. How is it related to the current? You know here d by dx is equal to minus I into rho into pi r square. You know d by dx, substitute the value, then cross multiply or rearrange, find out what is I. Can anyone tell me? Can anyone tell what is I? So to find I, what we can do? We know what is d by dx, potential gradient. Okay. So all these formulas you need to know. I wouldn't expect, I mean, it's difficult to by heart what is the potential gradient formula, what is the, what to say, the I formula, etc. It's always better you know d by dx, then you know the relationship with what is current, etc. So that you can, it will just take few minutes, might be less than 2 to 3 minutes just to derive it. That is much more easier than learning all the formulas by heart. That's why I'm showing this derivation. Okay. Because if you're by hearting it, there are chances that you will make mistake. I mean, you may forget or something because you have a lot, many other formulas also to by heart. And so if I rearrange this, I'll get I equal to minus m EAC naught by del tan HML pi r square. Now the next thing you have to know is what is impedance of the pore. So of a single pore, your impedance will be what? ESC naught by I. So ESC naught as such, and you know what is I. Please substitute and tell me what is the formula. So how can you proceed? You know what is EAC naught by I? What is I? I is minus m into EAC naught tan HML pi r square by rho. So EAC naught, EAC naught will cancel out. You will just, so finally you will get something of the form rho by pi r square hot HML by m. Now what I'll do is I'll multiply by L in the numerator and denominator. Okay, and then I'll just rearrange it. That is rho L by pi r square. Okay, you have cot h. I'm just introducing a dimensionless constant and writing raised to 1 by 2 and this raised to 1 by 2. Okay, this is nothing but it is a dimensionless admittance. Okay, dimensionless admittance. Okay, which value is ml square. Okay, now this rho L by pi r square, I can again rewrite it as, no, I'll just keep it like this. So this is the final expression for the pore impedance of a single pore. So this value, okay, rho L by this, that is nothing but resistance per unit length. I am just, sorry, not, I'll not write over here. So I'll just rewrite what I wrote now. So you have Z pore, which is equal to R. P is just indicative of pore. Okay, now this is dimensionless admittance and this one is rho L by pi r square. This is the next equation you need to know in solving problems. So the assignments are based on these three this thing, and one more is coming on the way. Okay, now what is this del square? Sorry, del raised to 1 by 2 is equal to ml. Okay, it's ml square. Okay, and if I'm just substituting it, it becomes j omega c dl 2 del 2 rho by r into L. Then I'm multiplying by pi r square bottom and up to just write it in a better version or simplified version. So and then when I rearrange, I'll get y CDL 2 pi r L rho L by pi r square. Okay, then finally you need to know what is Z total. So Z total, that is a total impedance, so which is nothing but it will be Z pore, you know the impedance of the pore. Okay, that's the total pore impedance by N will give you, okay, and R solution plus R solution. So these formulas you need to know, that is this one, which becomes your first formula. This formula is important, the second one. This formula is important, the third one. This formula, fourth one is important, and this formula, fifth one is important. So these many things, 5 formulas are important from this portion to solve the problems. I mean, you can expect questions based on this for your final exam, as well as in the assignment there are questions. Okay, we'll just look into that. Yeah. Consider a porous electrode. We'll just continue with the questions. Consider porous electrode, and we say that the potential is equal to 0 volt versus OCP and there is no reaction. When an AC potential is applied at the pore end, potential gradient is 0, potential amplitude is 0, potential amplitude is EAC not, none of the above. What is it?
This is a boundary condition, right?
Yeah,
So potential gradient is 0.
yeah. So that's what you can expect questions based on the boundary conditions also. For other derivations also you can something like that. So please look into everything. So it's not like derivation is not at all important. You can expect some questions from any of the steps. So that's why I'm also emphasizing on the derivation. In the above case, the electrode has 3 into 10 to the power 6 pores per centimeter square, and the radius of the pore is 1 micron, and with 400 micron pore length. Double layer capacitance is 20 microfarad per centimeter square. Conductivity of the solution is 15 ohm centimeter. Our solution is 10 ohms. Calculate the total resistance of the solution in single pore in mega ohms. Please do it. Can anyone tell the formula? What is the total resistance of the solution in a single pore? Please substitute the value and find out the answer. So what are the different values given? Have. So it's also like you should understand what each value is. You should be careful in converting the units, okay, and proceeding with the question. So yeah, you see it's ohm centimeter for rho. Okay, so it's better you convert L and R value also to centimeter unit. Okay, it is 15 into 400. So how do you convert microns to centimeter? Into 10 to the power minus 4, right? 3.14, 3.14 into R, that is 1 into 10 to the power minus 4. Square. Can anyone tell what is the answer?
19.10.
Yeah, correct. So if you solve this, you'll get 19.1 into 10 to the power 6 ohm centimeter square. And to convert with 2 mega ohms, you have to divide by 10 to the power 6. Okay. And finally, your answer will be 19.1 mega ohm centimeter square. Sorry, ohm, it's only in ohm, no centimeter square. Mega ohms. Okay, this is the answer. Any doubt, anyone? Now we'll go to the next question. In the above case, you have to calculate the admittance of the pore at the frequency of 1 hertz. Okay, so here, how will you do this? Basically, all the other values remain the same. What value? Like you have R as 1 micron, L value as 400 micron, right? That's it, right? Rho value. Rho value will be 15 ohm centimeter. Anyone, like, how did you proceed? What answer did you get? So, what is the formula for dimensionless admittance? Anyone? So, there's the formula. I'm just simplifying it. Okay. And what is YCDL? It is J omega C. You also need pi, sorry, you also need CDL value. CDL is given in the question as 20 microfarad per centimeter square. Double layer capacitance is 20 microfarad per centimeter square. It's given in the question. So I'm substituting all the value. J, what is omega? Just 2 pi, frequency is 1, 2 pi f, right? So 2 pi into 1, CDL is 20 into 10 to the power minus 6 okay, into 2 pi L. Pi and pi will also get cancelled. L equal to 2 into 400 into 10 to the power minus 4 by R. It's 1 into 10 to the power minus 4 into rho. Rho is 15 ohm centimeter. So into one more L. So L into L square. I'm just writing it over here. Okay. Now, how will I solve it? So, anyone, how did you solve for the assignment? You can either solve it in calculator. Okay, in calculator you do the root, you'll get it. So what did I do is I did it in MATLAB. Okay, for my easiness. So this is the code. Code in the sense I'm just typing it normally. I'm just assigning some values like CDL is 20 to 10 to the power minus 6. Rho RHO equal to 15. Length equal to 400 into 10 to the power minus 4 centimeter. Radius equal to 1 into 10 to the power minus 4. F value frequency is given as 1 Hertz. So you know omega is 2 into pi into F. Okay. Pi we can write as pi itself because MATLAB is able to read it as 3.14. F it will take from here. YCDL is J omega CDL. So J is the, again J in MATLAB is assigned to the complex number. So I directly wrote as J omega CDL. N is 3 into 10 to the power 6. Right? You're supposed to find out the admittance value, which is nothing but square root of YCDL, same as what we wrote over here. Square root of J into 2 pi. So you'll see, no, I've already calculated that. I calculate separately YCDL here. Then again, the next one was 2 pi RL. Everything is calculated separately. So YCDL into 2 into length square into rho by radius, the formula which I wrote in the PPT. And the mod of the admittance will be nothing but it's the absolute value of the admittance. That's what is asked in the question. I'm simply running the code. Okay. And the value. You can see that admittance I got as 0.1737 plus 0.1737 I. And mod value will be the absolute value. It's directly giving me as 0.2456. So finally, my answer is 0.2456. Were you able to follow that? Is there any doubt?
Here, square is not of 2, na? It is L square. So it is 400 into 10 to the power minus 4 whole raised to 2.
Ah, yeah, sorry, yeah, correct. 2 into 400 into 10 to the power minus 4 square into 15. So in the code I have written it correct. There I've found it out as 2 into length square into rho by radius. So here I've done correctly. There I just made that mistake. Is there any doubt in that? So I'll just give a hint on how to do the next question. We'll stop with that today. We'll discuss the next. I think 4 more questions are there, where 9, 10 if you do, 11th and 12th are just a repetition. You change the value and you get it. So how do you proceed with this? Here you get our solution value is 100 ohms. It's given. You're asked to find the real and imaginary part of the impedance of the electrode at frequency 10 hertz. So it's just the same as what you did in the last question, except that the formula changes. Here the R solution is given. Supposed to find out the total impedance, right? So what is the total impedance? You have total impedance as R solution plus Z4 by N. So if we have to find out Z4, what you have to do? You have to find out Z4, that is the impedance of the pore. You need to know what is that? That is R cot H raised to 1 by 2 impedance admittance is 1 by 2. You'll have to find out what is the dimensionless admittance. So for that you again know what is dimensionless admittance formula, that is same as this one. So once you know this, okay, here the different, you cannot use the same value as the previous one because here the frequency is different. Here it's a 10 hertz. Same thing you will do, but at frequency equal to 10 hertz. You will do it and you can get the answer. We'll discuss the later parts in the next class. Is there any doubt for anyone? So you understand, right? So all these questions are linked. So it's like, don't learn all that formulas by heart. There are 5 formulas I told you. Just learn the potential gradient, then try to derive. Like if you know dE by dx, you know how I is related to dE by dx. Just learn that kind of relation. Then impedance will be nothing but EAC naught by I. The I will be the one which you found from the previous case. After that, you will again simplify it. You will find out what is the dimensionless admittance. Okay. Then Z total will be R solution plus Z4 by N. So don't learn all those by heart because it becomes difficult. If you're trying to just derive it from there, if you're thorough with how to do it, it will take less than 2 minutes. So learn by heart only those which are needed to be by hearted. Don't by heart everything, then you'll forget things for the exam. Okay. Is there anything else?
Please, madam, if we continue that, how we get real part and imaginary part? J is there here?
Yeah, I can discuss it in the next class. So just if you want to see the solution, yeah. Again, I did that also in.
Yes.
So you know CDL, rho, length, radius, frequency, omega, YCDL, N value, everything. So here the frequency is 10. Everything else remains the same thing. Okay. So you know the admittance formula, that is square root of YCDL into 2 into length square into rho by radius. That's what you discussed in the previous question, right? After that you will find out mode admittance. So till this it's the same as before. Okay. Till this it is same as before. Now what you have to do? You have to, you know what is R solution? Z4. So Z total is R solution plus Z4 by N. So now you have to find out the Z4. How do you find out the Z4? Z4 is nothing but you have seen that equation. It is R into cot H dimensional admittance by dimensional admittance raised to 1 by 2, right? So that formula you will use. So how do you do that? Same thing I've written here. Resistance of a single pore into cot H admittance by admittance. Now, what is the resistance of a single pore? That is rho into length by pi by radius square. Substitute all that, you run the code, you'll get the answer. So yeah. So Z total equal to 102.12 minus 10.63 I. So this becomes your first question, ninth question's answer. This becomes your 10th question's answer. I'll discuss that in detail for the next class. Is that okay?
And if possible, please arrange 2 extra classes because this will be very helpful to us now. Examination very coming close.
So actually, like that is not in my hand. Like it was decided by the NPTL. Okay, not NPTL actually. So I am a PMRF scholar. So this is my TA duty, and as per that, actually we are supposed to take classes for 12 weeks. So this time they've also allotted us 2 extras. So that's how one more extra class is there. So I'll try to discuss the maximum for that class. Okay, so that's not
Okay,
actually.
but
Yeah, I understand that.
these are
So
all very helpful to us because
yeah, I understand that. So that's what sir is discussing everything, and like in each week you have something like 4 hours of video. So that's what we are shortening it and taking it in 2 hours. So that's again
but
difficult. It's difficult to complete that, right?
we get good understanding in these sessions rather than that.
Yeah, I understand that, but
For me,
I
it is
can.
right.
Okay, I understand that, but I cannot. It's not in my hands.
Okay, if possible, as many more classes.
Yeah, we'll. I'm not sure on that because we are like we are asked to like so actually it is 12-week class. So this time they've allotted us like an option. You want you can take 1 hour or 2 hour extra. So I said I'll go for 2 hour because some more portions are left to be completed. So yeah, mostly by next week next class 2 hours. What that's my plan. Non-linear EIS, I went through the video. So like there are derivations in that. Most of them are solved in MATLAB. So I'll just go for the brief outline on what exactly sir is teaching in non-linear EIS. I'll try to wind up it in 1 hour, and then I'll just give a brief summary of what exactly we learned in this 12 weeks. Okay. So yeah, and little bit of that PDM models also, just to understand what. So I'll just and yeah, little more time if I can take, I'll surely do that. Is that okay?
Madam, we have one doubt. Actually, if just request,
Hmm.
there is assignment number 11, question number 9, 10. Only
Okay.
EAC is given. They are asking charge transfer resistance.
So that is given in one of the video, right? Like how exactly we can predict the RT if like
Nothing is given there actually.
actually that's a link to question, right?
No, that is assignment number 11,
Okay, I'll
right?
just discuss with sir and let you know.
Okay,
Assignment 11.
okay,
Okay.
okay,
Yeah. Okay.
Sir
okay.
had also
Please.
accepted the fact that it is insufficient
Okay,
Yes, yes.
okay. Okay,
information given,
then the mark will be
and
given
he
for
had
that.
given yes, and
But
he had
if
given extra information also. He has given in one particular email.
Okay.
yes, yes.
So in that case that will be marked as 0 mark. I mean, you will be given mark for that. That question will
But
be nullified.
we are not finding any derivation like that in book also, right? In search lecture also. If
Yeah,
EAC is given, how to
okay,
find
so that's what,
nonlinear charge transfer
so like
resistance?
someone told like it is an insufficient data. I have not gone through the assignment. Like when I went through, I could see that resistance to charge transfer questions are there. Apart from that, everything was theory is what I saw. So like if sir has told that it's an insufficient data, then mark will be provided to everyone. That question will be actually neglected when calculating your total marks.
Okay, okay, no problem. Mass, I'm not asking mass.
Ah, yeah,
How
okay,
to
fine.
solve this problem? That is the question, right? If
So
such
if
problem came, how
yeah,
to
so
solve? Few
if that is
questions.
insufficient data means then it's not possible to solve. I'll look into it and I'll let you know.
Okay, okay, thank you.
Yeah, next class I'll answer that. Okay. Okay, thank you everyone. I'm stopping today's class.
Okay, thank you.
Thank you.
Thank you.